Welcome back to Artificial Neural Networks. We've just discussed the ability of one neuron to perform the operation of the logic gate AND. Did you figure out how? Let's see together what this process looks like. First, let's define the elements of the operation numerically. We will represent true as the number 1 and false as the number 0. Here we have two dendrites. Those are our input elements. Let's say that in this problem our synapses are adjusted to 0.7 and 0.5. The threshold above which this neuron will fire an output is adjusted to 1. As you can see, only if both dendrites received true or 1 as input from the axons of other neurons, this neuron will fire. In the context of a network, this means it will pass the message to yet another set of neurons. What happens if we'd like to change it to the OR logic gate? First, we increase the strength, the weight, of these synapses, let's say to 1.1 and 1.3. Now, it's enough that only one input will be 1 for this neuron to fire. It could also be that both of them will be 1 for this neuron to fire. But it's not possible for none of them to have 1. This is exactly the OR gate. What about more complex tasks, or even just more complex logic gates? For example, a very important logic gate is exclusive OR, called XOR. This gate requires that only one input will be true, but not two of them. Only then the XOR logic gate becomes true as well. How can one neuron perform this operation? Well, it can't. But 3 neurons can, if they are constructed in 2 layers like this. With this structure, only if the first input is 1 and the second one is 0, or the other way around, the last neuron will fire. If both inputs are 1, the last neuron will not fire, nor if none of them are 1. Do you see where this is going? We added another layer and received a more advanced computation capability. Let's try to visualize this phenomenon. This matrix represents the logic operation. Each dimension, rows or columns, represents one input, which can be 1 or 0, true or false. The values in the matrix represent the output. The logic gate AND will look like this. Only if both inputs are 1, the output is 1. What we can imagine is that a perceptron is like drawing a separation line between the region of true and the region of false. If we change it to the logic gate OR, this imaginary line just moves up a bit. As we've seen, the required behavior is implemented by increasing the weights of the synapses in the perceptron. Actually, this separation line is more than just an imaginary aid. It's really the mathematical abstraction of differentiating between 2 regions in a solution space. Now, what needs to be done if we want to compute the logic gate XOR? We need 2 separation lines. And the structure of the neural network with 2 layers that we've just seen achieves that exactly. So again, just by adding a layer of neurons, we received a more advanced computation capability. Similarly, we can add more and more layers between the input layer and the output layer. These are called hidden layers. Each layer can contain many neurons. If we look at this input layer, the fact that it has so many dendrites means that we can give the neural network a larger input. The input can be in form of a vector of numbers. It can be even a complex vector that represents data of many kinds: numerical, visual, vocal, even textual. This multi-layer architecture is amazingly similar to how our brain neurons are wired. They also receive different kinds of inputs from our eyes, ears, and other sensors. But that's not all. whatever created our brains, some say God, or evolution, maybe aliens, whoever sat and adjusted the strength of all the billions of synapses in our brain gave us another crucial capability. This is maybe the most important ability of the animal kingdom, the capability to learn. Maybe also the capability to think, to hypothesize, to infer, and so on. With the computing power of today, we can create artificial neural networks of tens, hundreds, and millions of layers. These amazing computational capabilities enable algorithms also to learn, infer, and so on. More than anything, this capability of neural networks is what makes it so powerful, so successful, and what leads us more and more to the holy grail of strong AI.